In the sessions 2, we come to the detailed definitions regarding a continuity and the limit of the function and the differentiability, and give us some examples regarding a continuous functions and differentiability functions. So we already know in the real functions when when the function is differentiable, when the function is differentiable, when the function is continuity. See, here a complex number w of f of z is defined as a function of complex variable z. For every value of z, it contain a region corresponding to one or more values of w. I say contain one or more values of w. See, the same is word in field of this functions word in field of real functions. Say a complex number w of f of z is defined as a function of complex variable z. If for every value of z in a certain region correspond to one or more values of w, this definitions is same model as usual definition of functions of real variable. See, what I'm saying is what you define in the real variable, the same hold in the complex variable. See, what definitions hold in the real variable, the same definitions hold in complex. But this complex are defined in the unit circle form, that is x plus I y, which the limit hold in that unit or unit circle form. So this is the limit hold that. So continuity holding like that. So this is the same word in the complex variable word in the real. What's a real variable? It's the same field in word in complex variable. Therefore, the definition of continuity for a functions of complex variable is exactly same as that functions of a real variable. Thus, the continuity of a functions of complex variable. The definitions: a function f of z of a complex variable z defined in a closed and bounded domain D is said to be a continuous at z0 belongs to D. If and only if for every arbitrary chosen a positive number epsilon, however small but not zero, there exists a corresponding number delta positive such that mod f of z minus f of z naught less than epsilon whenever mod z minus z naught less than delta. See, this is the, so you are observing the real, the same mode in the complex there. But you are in the complex, we are defined the reason and bounded the reason, bounded the domain. Bounded domain is if you take a unit circle in the complex form, see all the point in the complex unit circle. We define that functions. So if you take any arbitrary positive number, the difference of f of z minus f of z are less than that. The epsilon value should not be 0 because a difference should not be 0. Then their corresponding number we take the delta positive such that mod f of z minus f of z not less than epsilon whenever mod z minus z not less than delta. See, so we know that. So when the function is continuous, the limit point is exist. Limit point is exist at a point z equal to z naught. So if it exists, certainly we can write that function should be that. Means we know in the real. If a limit extends to a mod f of z minus f of z naught less than something. So this exists. Certainly we define at z equal to z naught and limit z tends to z naught f of z exists, then limit z tends to z naught f of z equal to f of z naught. This is the continuity of a function. We say that f of z is a continuous function in a domain D if it is continuous at every z belongs to D. It can be easily shown that f of z equal to u of x comma y plus I v of x comma y is continuous a function of z if and only if u and v are function of x and y. See, here you are separating here reality and imaginary part. So reality and imaginary functions, u of xy is a function of that. So here complex number as a functions. We are express in terms of u and v in terms of x and y. So u and v is a function of x and y. So define that u is a complex variable and v is a complex variable. But u is contain x and y. V is also contain x and y. So u is a real part. Then v is an imaginary part. We can define. So for I given some problem particularly examples right. First, so that does if f of z equal to z square plus 2z is a continuous at 1 plus I. So 1 plus I is a complex number. So we are complex number. So limit z tends to 1 plus I. Z square plus 2z equal to 1 plus I whole square plus 2 times of 1 plus I. So we simplifying that. So we get 1 plus I whole square is a plus b whole square formula. We get 1 square plus I square plus 2I plus open that 2 plus 2 plus I. Again we get I square is minus 1, 1 minus 1 get cancelled. Then we get 2I plus 2 plus 2I. We get 4I plus 2. So again a expressed in complex form 2 plus 4. In another way we can say if I replace a function z, if z is 1 plus I, f of 1 plus I equal to z square plus 2I means replace 1 plus I whole square plus 2 times of 1 plus I. Simply we can simplify, we get the same result 2 plus 4I. Thus the limit z tends to 1 plus I, f of z equal to f of 1 plus I is both are equal. Hence the given function f of z is continuous at 1 plus I. We take a second example. So that f of z equal to xy divided by x square plus y square, z not equal to 0. If 0, z equal to 0 is not continuous at the origin. See, in the horizon is V1. Suppose if you take it, so z tends to 0 along a path y equal to mx. Now, limit z tends to 0, f of z equal to limit z tends to 0 xy divided by x square plus y square. See, if a limit z tends to 0, if you replace f of z, see a path in the term f of z of that should be replace y by mx. We get x into mx divided by x square plus m square x square. So x square get cancelled in the both the numerator and denominator. We get m divided by 1 plus m square. Yeah, see, both numerator and denominator in terms of m. Yeah, m is independent. Depend on m is independent. So the values of limit is depend on m, which is not unique because m divided by 1 by m square, which is not a unique. So you give any value for m, we get a different. Does not cancel. Does not get cancelled. So this m, this term depend on m, which is not unique for different values of m. Hence the limit does not exist, and therefore f of z is not continuous at z equal to 0. So in the first example I saw in the continuous. In the second example is not continuous. Do you know the difference between when the function is continuous and the function is not continuous? One more example I am taking, so that the function f of z equal to x cube of 1 plus I minus y cube of 1 minus I divided by x square plus y square for z not equal to 0. 0 for z equal to 0 is a continuous at the origin. The same way I express the term x cube of 1 plus I minus y cube of 1 minus I divided by x cube plus y x square plus y square. That's right. Again I am separating here real term and imaginary term. Real functions and imaginary. U of xy form like that. U of xy plus I v of xy. So I'm in the numerator I open the bracket. We get x square minus y square. X square x cube minus y cube of I take whole term I terms of x cube plus y cube divided by x cube plus x square plus y square. Again I am separating real and imaginary term. X cube minus y cube divided by x square plus y square plus I terms of x cube plus y cube divided by x square plus y square. Again, the complex f of z can be written w equal to f of z equal to u of xy plus I v of x. So again, we are separating the term and minimizing the same way. See, if we come to the differentiability, see, you are not limiting the same. So function we know limit, continuity. Now we come to the differentiability of a complex variable. See, the same and hold in the field of real number, the same hold in case of complex variable form. See, what's the differentiability in that? See, since the same mode of definitions of a continuity is the same, both the case of the functions of real variable and complex variable. See, I can once again, I'm saying, since the mode of the definition of a continuity is same, both in case of functions of real and a complex variable. Therefore, the definition of a derivative of a complex functions of f of z is identical with the definition of derivative of a real function. Hence, the succession is the differentiation. We write limit z tends to z naught f of z minus f of z naught divided by z minus z naught. Or we say in the definitions form, in the what's in the reality, real, the word in the complex variable. Let f of z be a functions of complex variable z defined in a domain D, then f of z is said to be a differentiable at a point z naught of a D. If and only if limit delta z tends to 0, f of z naught plus delta z minus f of z naught divided by delta z. Or limit z tends to z naught, f of z minus f of z naught divided by z minus z naught exists finitely is called derivative of f with respect to z at z equal to z naught. Usually it is denoted by f dash of z naught or d of f of z naught. See, this is same in form of real, in the real form of that. See, the same. So limit x tends to a function f of z is a function of complex variable. Then we see if we take a limit z tends to z naught f of z minus f of z naught divided by z minus z naught. This is called derivative of z naught at z tends to z naught, usually denoted by derivative f of z naught. If we get a different value of this limit as z tends to z naught from the different point of z, that is, if the limit depends upon the absolute values of amplitude of delta z, we say that the derivative of f of z at z equal to z naught does not exist, and the function f of z is said to be non-differentiable at z naught, z equal to z naught. Hence, in order to prove a non-differentiability of f of z, we should try a different path for delta z, convenient path for delta z, or along a real and imaginary axis by taking delta z either whole real or wholly imaginary. So, real or whole imaginary, the same, we are giving some examples regarding the functions is differentiable or not differentiable. See, so I take an examples using the definitions and find the derivative of f of z means f of z equal to z cube minus 2z at z equal to z naught. By definitions, the derivative of at z equal to z naught is derivative of z equal to, I apply the definitions, limit delta z tends to 0, f of z naught plus delta z minus f of z naught divided by delta z equal to limit delta z tends to 0. So replace the function z is z naught plus delta z. See, replace z by z naught plus delta z. So z cube we get z naught plus delta z whole cube minus 2 times of z naught plus delta z minus, again replace z by z naught minus 2 delta z divided by delta z. Again apply a plus b whole cube formula, we get a cube plus 3a square b plus 3ab square plus bq form. Same way, z naught cube plus 3 times of z naught square delta z plus 3 times of z naught delta z square plus, again open that, delta z whole cube minus 2 z naught minus 2 delta z minus, I open that, minus z naught cube plus 2 z naught divided by delta z. Again, as simplifying, here z naught cube get cancels. Again, I collecting z naught square. Again, one term delta z I take, that term get cancels. Simply delta z some term get cancels. We get 3 z naught square plus 3 z naught delta z plus delta z whole square minus 2. So you are applying here directly a limit. Replace delta z should be 0. We get 3 z naught square minus 2. So if you replace z naught square 0, you term get cancels. You get 3. So z naught is same as z because z tends to z naught. Why like that? So replace z naught by z, we get in generally derivative f of z equal to 3z square minus 2 for all z. I give one more example. If f of z equal to 1 plus z divided by 1 minus z, find the derivative f of z. So in the same case we apply limit derivative f of z equal to limit delta z tends to 0. F of z plus delta z minus f of z divided by delta z. So replace z by z plus delta z. 1 plus z plus delta z divided by 1 minus z plus delta z minus 1 plus z divided by 1 minus z. The whole divided by delta z. Again, apply cross multiply 1 plus z plus delta z into 1 minus z minus 1 plus z into 1 minus of z plus delta z all divided by 1 minus z into 1 minus z plus delta z. So simplifying, so rationalizing, simplify, we get the limit delta z tends to 0, 2 divided by 1 minus z minus delta z into 1 minus z. Yes, yeah. So now that numerator get, only numerator will get 2 divided, denominator get 1 minus z minus delta z into 1 minus z. So you replace delta z by 0, we get 2 divided by 1 minus z into 1 minus z. Suddenly this equal to 2 divided by 1 minus z square. Yeah, this independent of manner in this delta z tends to 0 possible. Here z not equal to 1. If z equal to 1, suddenly this is not defined because we get a, so z is not equal to 1. This is the function we are defined is independent of this derivative. Simply we get one more, the same term we are expressed in term. If f of z equal to x cube y of 1 minus ix divided by x to the power of 6 plus y to the power of y square at z equal to 0. So if a function f of 0 equal to certainly 0, then prove that f of z minus f of 0 divided by z is 0 as z tends to 0 along any radius vector but not z equal to 0 in the same manner. In the same manner in the epigenetic. The same problem we apply for this is the same. If you replace z tends to 0, apply for f of z minus f of 0 divided by z. So apply this, we get minus I divided by 2. The similar, the same manner we apply this problem, we solve that. So yeah, the problem is same for reality, real form, real functions form. But what the limit, what the derivative exists, the function you are apply what limit is given. Limit is given in the form of complex number. Okay.